Good morning or good afternoon, everybody. This is Mr. Steele, once again here to provide you one of the lectures while I'm out with after back surgery. In today's lecture, we're going to focus on the concepts of concavity and points of inflection, two very visual properties that a function or its graph will actually possess. But of course, before we get there, those terms might not sound familiar, so we're going to start by giving you some context. In fact, in today's lecture, my goal is to begin by giving you some visual context for what concavity is, to kind of show you some little pieces there and kind of connect it to some things that we might be able to see a little bit better. We'll move forward and talk about the definitions of concavity, including a couple different ones, and show you some motivation that helps you grab some connections between concavity and the first and second derivative of a function. Then we'll do the same with points of inflection. We'll introduce something called the second derivative test. And then finally, we'll bring everything together in a couple problems, a few that I'll do and a few that you will do. So without further ado, let's jump into the first part of the lecture. So as you can probably already see, probably have already seen, I'm starting by asking you to consider a particular function, which is a positive cubic function, x cubed minus 6x squared minus 36x plus 216. And my goal here is to start with something really simple to illustrate and give you a visual context for what concavity is, like what it is specifically. So to start with, I think it would be pretty helpful if I factor this for you. I don't expect you to do this. It's not a clean, easy factor. Let me make sure I do it correctly. This factors to x plus 6, x minus 6 squared. So this is the same thing as f of x, just factored. And that means that if we desired, we could actually write this whole thing or sketch this function out really nicely. So there would be our function. Based on what's here, this would have to be negative 6, and this would have to be positive 6 for what that's worth. So there is our function. Pretty standard, in Franklin terms, positive noodle, right? Nothing really crazy there. Although I did a poor job making it smooth, but setting that aside. So from here, I submit that there's some information hidden in here, and one way that we've accessed information about like the properties and behavior of a function in the past has been to compute the derivative. And that's not too bad. It's a pretty clean derivative to compute. Polynomials tend to be helpful in that way. And for the sake of saving some time, let me just point out to you that this will factor into x minus 6, x plus 2, all times 3. So of course what that gives us is a pathway to figure out where the critical numbers are. In fact, in this particular situation, there are two critical numbers. They're going to be at x equals 6 and x equals negative 2. And we know from the work we've done in the past that that means that we will correspond to our relative extrema, or could potentially respond to our relative extrema. In this case, that means we have negative 2 right there, and of course 6 right there, and it looks like we found two relative extrema. Now here's the thing though. If we take things one derivative further and compute the second derivative, in a sense, we're just analyzing the first derivative, right? We'd just be figuring out where there's relative extremas on the first derivative and all sorts of stuff. So for our sake, let's go ahead and calculate that. F double prime would be 6x minus 12. And since setting derivatives equal to 0 is just a kind of the in vogue thing to do in Calculus AB right now, you could very quickly figure out that there's something happening at, I'm just going to even write it this way, since we don't have names for things just yet, something at x equals 2. So allegedly, when we look at this graph, there should be something that's happening at x equals 2. Like there's got to be something changing. Like for instance, if we look at where f prime is equal to 0, we figure out places where f changes from increasing to decreasing. Well, something has to be changing at x equals 2. So I guess my question is, can you tell what the difference is between things on the left of x equals 2 and on the right of x equals 2? Do you see any difference? And to help us do that, I'm going to sketch what's on the left. And so this is when x is less than 2. And then on the right, when x is greater than 2. So in looking at these two expressions, especially with the way I've written those inequalities maybe in there, how would you describe the difference between the left curve and the right curve? Like what would be your description there? Like could you say anything? So normally in class I would facilitate a quick little discussion asking you to throw out ideas and describe things that are there. But I am sad that I can't be there to participate in a happy discussion. Did I maybe just trick you into seeing exactly what I'm seeing? here's what I'm going to throw out there. Like, visually speaking, I know people like to say maximum on the left, minimum on the right, but let's draw a couple eyes on there. Maybe even draw a nose. It's your call. Give a beard, since I'm the one that's stuck at home unhappy. So hopefully what you're seeing is on the left, we have something, and this seems very non-mathematical, and it is, but just play along for the moment. On the left, we seem to have something that's sad, and on the right, we seem to have something that's happy. And of course, when you think of sad, if I asked you to associate sad with positive or negative, you'd say that something's negative. And if you said something was happy, you would probably say that it's positive. And the truth is, this is absolutely what we're looking at here. On the left side, the thing seems to be opening downward. It's oriented in a downward direction. On the right side, it's oriented in an upward direction. And at x equals 2 itself, something is changing. Like, we're changing from one value to the other. So in a sense, what we've got is our visual for this thing that we're going to be calling concavity here. And a good way to think about concavity is it's kind of like a certain animal. So let me draw a nice animal for you, because I'm sure you love my animal drawings and have missed my inability to art for quite some time. Let's see if I can do this right. Okay, this probably looks like a dinosaur. Okay, these are legs down here. Okay, I'm realizing that I'm really terrible at drawing pictures of animals. What animal is that? If you said camel, you are the winner of absolutely nothing, but that is the animal that I just drew. I drew a camel, and the reason I drew a camel is because when you think of camels, you naturally think of their humps, where they sit on where people can sit on the back or sit between on the back, where I believe they store water, although again I'm not a biologist or a zoologist. But basically those humps can be described, can be a good apt way to describe what we're talking about here with this thing called concavity. Like, it's the directionality or the orientation of the humps of the actual graph that we're looking at. So think about that for the moment, like get that idea in your head. Today we're talking about humps like a camel would, probably on any day. So keep that in the back of your mind. Again, kind of a weird way to start, but let's take a look at some definitions then. So if we want to talk about this property that has to do with sad and happy faces and all sorts of things, we need to actually go through and do more than just draw dots on our picture. So here we go, definitions. So the first definitions I have here, which you are welcome to write down, and I'd encourage you to write down. In fact, you may need to pause the video at some point here. Both talk about like what it is that's going on. So first and foremost, at the very top, I mentioned concavity itself. Concavity is described as the directionality of a curve or the hump directions for those parts of the curve. And now it's a little bit hard because we're not always going to have like fully formed like literal camel humps like that. Sometimes it'll just be a little piece, but you would imagine in that case to talk about its concavity by drawing it in that, by drawing in the rest of the curve and then finishing from there. So with that in mind, there are two different types of concavity, as you can probably figure out already. So the first of those possibilities is that a curve might be concave up. And as it says here, assuming f is twice differentiable, the graph of f is concave up if all tangent lines to f are below the graph of f of x. So to illustrate what I mean, let me draw a very clearly concave up function. So there is something that's clearly concave up. Now if we try to draw a tangent line to this curve on the left, again it's not going to be perfect because of my inability to draw, but notice every curve, or every tangent line to that curve, is actually below the graph, the entire graph on that region. And again, we did set it for a finite interval, finite open interval, but it looks like all the tangent lines are clearly below the curve. So that is concave up. On the flip side, we have concave down. Concave down reverses the direction of that statement. So concave down for an interval a to b is when all the tangent lines to f are above the graph of f of x. So for instance, if I draw my tangent lines here, notice that any tangent line I draw appears to be above the curve for all values along that curve. So now I know my pictures aren't perfect, and more important than that, I know that those definitions are a little bit wonky. It's a little bit weird to make that your quality. We're used to a little bit more punchy. But just to confirm that this is accurate, let me show you what this actually looks like. So here is a clearly concave up function, and here are tangent lines to that curve. So if I let that play, notice that no matter where that tangent line is on this concave up function, the tangent line is, let's make sure I put this on there, the tangent line is below the curve. It stays below it that entire time because this function is concave up everywhere. Now with that said, flip that on its head, I'm literally going to flip it, and take a look at what the tangent lines do for this concave down function. So setting aside the fact that it takes a little while for the curve to actually appear to be touched by this, there it is. Notice that the tangent line is above the curve everywhere. So at the very least, like, you can see that this description that we have, this like kind of definition, does seem to be visually supported. Looks like it's a pretty accurate thing. Like, I'm not too worried about that myself. So good deal there. But now comes the bigger problem. Like, just because that's our definition doesn't mean that's easy for us to tell. And more importantly, how could we mathematically show that? You're not going to convince me that something's concave down just by drawing a picture and going, see, no matter where I draw a tangent line, it's going to be above the curve. Like, that's not going to work. So instead, we need something that's a little bit more formal. So at this point, what I typically do in this lecture is I invite students to pull out your graphing calculator. So if you have one, feel free to pull one out. Pull it out right now. So we're talking about concavity, this thing called directionality of a curve. And in fact, we've looked at this graph, this function over here. Like, this is our curve that we looked at on that first page. In fact, I'm going to move it up to the very top corner here. We've seen our curve. And based on that description that we had before, like if we go through here and imagine trying to draw tangent lines, you can see that everything to the left has tangent lines above the curve, which means that we are concave down, or something. On the other hand, the tangent lines are below the curve on the right, which would meet our definition, and therefore mean that we are concave up. Ignore everything. There we go. So in here, what I want to point out is that based on our function, we have something happening at x equals 2. Let's do this correctly. We're going to calculate some values in just a second, by the way, so just bear with me for the moment. So what we have is we have that right here something changes. We haven't exactly figured out what it is just yet, but something changes at x equals 2. And then otherwise, what we can tell from looking at our picture is it appears that we are concave down to the left. Sorry, let's make sure we say this correctly. F is concave down. And then to the right of x equals 2, F is concave up. These are just the properties that we can tell are there. Same thing down below. F is concave down, and then F is concave up. Now the question to ask is, well, what does concave up or concave down mean about the derivative f prime? And then second, what does concave up or concave down mean about the second derivative f double prime? So what I would typically do is I would invite you to go through and calculate out a whole bunch of values of this function, either by using the derivative feature and splitting this up across the class, or by going through and taking into account what f prime and f double prime of x are equal to. In fact, I think we had these before. So for the sake of time, I'm going to magically snap, and I'm going to spit all those values down, so that way we have them so we can talk about them and analyze them. But again, keep in mind it'd be great if you were able to do this yourself. So ready? Boom. See it? Oh, look at that, they popped up. I'm glad, that was a lot better than the time Thanos snapped. Jeez. So, with that said, what we've got now are a bunch of values for both f prime and f double prime inside those regions where f is concave up, f is concave up, or concave down. So given that information, the question we want to look at is what's happening. Like, what's true about these pieces of information for each of the functions. And you know what, I've already got green going. Let's start with the f double prime down there. So at x equals 2, notice that the second derivative is 0. That's really nice. At x equals 2, the second derivative is 0. We said something was changing there, so maybe that 0 has something to do with it. To the left of x equals 0, so for x values less than 2, what we're seeing is that f double prime is going to be negative. So all the values of f double prime are negative. On the right side, on the other hand, all the values of f double prime are positive. Am I sure? Yes, I'm positive. So given that, what it seems like that's telling us is that f double prime is negative. Here, I'll just write it this way. We don't need to write that there. Looks to me like it's saying f double prime is negative when f is concave down, and f double prime is positive when f is concave up. So that's a pretty powerful thing. And in fact, I'd love to add that to my definitions on the next page. So if you could, please add to your definition for concave up that an alternate definition is that f double prime of x is greater than 0, or you could say f double prime is positive. Likewise, we can say the analogous statement that f double prime of x is less than 0, or f double prime is negative when f is concave down. So in a sense, what we've just gotten is the clearest, most common definition or connection for concavity. If you want to tell where a function is concave up or concave down, you can absolutely check and see what the second derivative is doing there. And to illustrate this really fast, let me pull up one of my favorite Desmos creations here. So let me go grab my function. There's the one that we've been analyzing. And what I'm going to do is, let me get rid of that extra negative sign. What I'm going to do is I'm going to go ahead and plot the second derivative for us. So here's the second derivative. I'm going to go ahead and label it for us. So ignore that point. That point's not huge, but at least now it's there. Why does it not want to be visible? Okay, there we go. So there's the second derivative. So now as we go forward on our graph, notice right now the second derivative is less than 0, meaning the second derivative is negative. Along this line, notice that we're on the section of the graph that's clearly concave down. Second derivative negative, concave down f. Now notice as the second derivative close to 0, we seem to be there, right there, where it literally equals 0. Our second derivative's value is 0. After that point, as we continue forward, where the graph is concave up, notice our second derivative is actually positive. So in other words, what we're seeing is pretty accurate. It looks to me like that's exactly what's true. When f is concave down, the second derivative is negative. When f is concave up, the second derivative is positive. So there is our first kind of visual confirming the same thing. So we've got this really nice connection between f double prime and f, as far as concavity goes. Now, we also looked at f prime, or at least I snapped into existence some information about f prime. So let's see what f prime is telling us. So once again, looking at our value, we know something special is happening at x equals 2, and looking down at all those values, it looks to me like negative 48, the slope of f at 2, is actually the minimum value. So it looks like f has its minimum slope at x equals 2. To the right of it, our values go negative 45, negative 36, negative 21, 0, 27. So what I'm seeing is those values are getting bigger. So in other words, f prime is increasing. And let's see if on the other side, we go 0, negative 21, negative 36, negative 45, negative 48. Since our values are getting more and more negative, that tells me that f prime is decreasing. So what we're seeing is a second way that we could talk about concavity by connecting it this time to f prime. What's happening is when f is concave down, the slope is decreasing. And now decreasing doesn't mean the magnitude is getting smaller, it just means that the slope is getting more and more negative. We're getting further and further away from 0. Likewise, when f is concave up, it looks like the slope is increasing. And so what we've got is our second definition here. So adding it in, we can also say that it's when f prime of x is increasing. That means that f is concave up. The slope is increasing. And then parallel, f prime of x is decreasing when f of x is concave down. And to illustrate this one more time, just kind of giving you another one of the visuals, go back to my little concavity piece. I feel like you might need to pause that, sorry. In case you need to write it down, give you a second there. So f prime decreasing, concave down, f prime increasing, concave up. Now from here, if I also graph the first derivative and plot that on our, that's I don't need y equals f prime. Oh, there we go. So if I plot that, okay, so taking into account for a second what's actually happening here. So in blue up here, we have the derivative f prime. So as we start on the left side where f is concave down, notice that the derivative is clearly decreasing. It's getting much smaller. Then it kind of slows down, kind of reaches what looks like a minimum at x equals 2, and then it starts increasing again. And simultaneously, of course, the second derivative is positive. It's at x equals 2 where everything kind of lines up, f prime's at its minimum, the second derivative is 0, and then after that, it begins to move forward. So once again, we've got something there. And since we've had tangent line in the past, just take a look. I mean, obviously there's going to be a lot of movement on here, but notice that our tangent line slope is above the curve, then it's slowly below the curve as it moves forward. Looks like all these different pieces do in fact add up the way we were expecting them to. So a little bit complicated, but I think what you're seeing here is we've now got a really good grasp on what this means, and we've got a more practical way to tell if a function is concave up or concave down. In particular, although we are going to have moments when we're going to use the f prime increasing or decreasing, particularly in tomorrow's lecture, let me point out to you that the key spot, the key thing that we're going to be using most of the time, is we're going to be using f double prime sine, because it's easy to analyze sine, particularly for a function where it's easy to compute the second derivative. And once we have that sine, we can very quickly determine whether or not the function is concave up or concave down, without having to actually see it, or check where all the tangent lines fall. So, interesting enough. But without further ado, let's go ahead and jump into a first example. Just because I know it's a lot of information, I want to make sure you realize just how doable this actually is. So here's our first full example here. I am going to ask you, or we are together going to, determine the x values for which the graph of f of x is concave down. And I'm asking you to justify your answer. And our function is another polynomial, again, just to kind of get our bearings here. We'll get a chance to play with some more difficult functions later. But our function f of x is negative x cubed plus 12x squared plus 45x minus 1. And we want to see what's actually going on here. So as we start, I'm going to throw a plan in here just because we might as well while we're here. I don't think this is necessarily a difficult one to go through, but let's throw a plan in there. And that plan is going to begin by computing our second derivative. And again, you can tell that this technique isn't necessarily practical because, of course, getting a first derivative can be hard, let alone a second derivative. But assuming that this is something that's reasonable to calculate, compute the second derivative first. So in order to get to the second derivative, though, we're going to have to first go through the first derivative. So make sure you don't get distracted as you do this first derivative and then start doing critical numbers. That's not what we're looking for here when we're asked to determine where the function is concave down. So in our case, this first derivative is going to be negative 3x squared plus 24x plus 45. Someone else can factor that thing. We're interested in the second derivative, which in our case is negative 6x plus 24. So our second derivative is present. We're ready to start taking a look at it. Once the second derivative is in our hands, of course, we want to find the places where it could change signs. So in other words, we're probably going to set f double prime of x equal to 0, but it could also be a spot where f double prime is undefined, so we're going to need to look for where those places are. Like, we'll have a name for what these points are in just a few minutes, but for now we're just looking for that place. So here we had a polynomial, we know it's infinitely differentiable and everything, it's all good there. If we set this thing equal to 0 though, we'll get one place where the sign of the second derivative is going to change signs, and that's going to be x equals 4. So in a sense, that's almost like our candidate or our critical number for the second derivative. So with x equals 4 in hand, we're interested in figuring out and determining the sign, S-I-G-N, of the second derivative. So once again, just like yesterday, we can make a sign chart. So we can draw it out, test some values, and see where the second derivative is positive and where it's negative. So in our case, doing a quick little sign chart here. You've probably figured out already I'm not very good at drawing straight lines. Oh, come on, really? It's gonna do it again? Of course it is. Oh, that's life. Okay. There. So in this sign chart, we want to check some values of f double prime, and particularly know the sign. We're going to split it up in the middle at x equals 4, where we know the second derivative is 0. And then we're going to check some values where x is less than 4, and some values where x is greater than 4. So in there, to do our sign chart, I'm just going to change my color here really fast. Make it a slightly darker red. There we go. Boom. So in here, if we check some values, I'm going to pick 0 as one value, and I'm going to pick 40 as another. If we plug in 0, we're going to get negative 0 plus 24, which is clearly positive. And if we want to plug in a value like 40, we're going to get negative 240 plus 24, which is clearly negative. So based on that information, we've completed our sign chart. Now it's just a matter of answer and justify. We just need to state what our intervals are and then justify our answer. So in looking here, looking at our expression, we can see that f is concave down. Remember, we were only asked about concave down. So f, or f's graph, is concave down. And it's for all the x values that are greater than 4. So of course you could use interval notation as well. Both are equivalent and fine. F is concave down for x greater than 4. And our reason is because f double prime is going to be less than 0. And there is the answer to our question. So nothing super difficult to get to, but it allowed us to quickly analyze our function and move on from there. So a couple things here. First and foremost, of course, this can move really, really fast, and it did move pretty fast, in fact. And I recommend, again, that if you're going just for concavity, like, don't dwell on the first derivative. It's just kind of distract you from your purpose. Second, though, I do want to be honest with you. If I was doing this problem, I would have gotten to this point, and then I would have not done a sign chart. Now, here's my reason why. Picture for a second what this function looks like. And again, it's a polynomial, so it's a pretty easy to work with function here. We have negative x cubed plus stuff with smaller degrees. That negative x cubed leads me to realize that this is a negative noodle. And again, made the joke before about sad spaghetti. But at the same time, if this is a negative noodle, we know that negative noodles behave like this. And the reason this is so helpful is that we can very quickly see that our function is concave down to the right of the critical, or of the point of inflection. Right. Oh, we don't know what that is yet. Right of that spot. It's hard not to describe it as what it is. So it's concave down to the right of that point, whatever it is, that place where the second derivative is 0. So basically you could save yourself a bunch of time if you know how the function's behaved, and just think your way through it, and then justify using the same technique. But again, just keep in mind that if you want to work through a sign chart, sometimes it'll be necessary because the problems are pretty hard to work with. But if you want to, go for it. I highly recommend it. It's a good organizational strategy in general anyhow. So, with that said, you notice that I accidentally slipped and started talking about that place where the concavity changed, and I called it something. And without further ado, I should just give you the name so that way we can move forward and describe these things more readily. I don't want to keep describing it as that place where the concavity changes. It's better just to give it a name, like Ted. Just a good name. So here's what it actually is. We call that place a point of inflection. It's a point of inflection, or often it's called, you've probably heard this phrase before, seen it on stuff. It could also be called a POI, a point of inflection, not a private octopus investigator. Don't get confused. So a point of inflection is a point C, f of C. And the reason I point that out, is because it means the graph has to exist there. And so what that means is you can't have a point of inflection at a vertical asymptote. Like if there's a vertical asymptote on your graph, there's no POI because there's no actual point there. That's just a boundless growth at that moment, or as you approach that moment. So for us, though, now that we've established the fact that it does have to be a point, you have a point of inflection at C, f of C when f double prime of x changes signs, or when f prime changes from increasing to decreasing or decreasing to increasing. So basically, for the moment, we're not going to worry so much about f prime changing from increasing to decreasing or decreasing to increasing, although you should absolutely write it down. Our focal point is going to be on that first one right here, simply because in our examples today, we're going to have good access to the second derivative. Should always be able to find it. So with these points of inflection, they're usually pretty easy to point out. So let me draw a couple examples here where you can see it happening. Because again, we're looking for a place where the function changes concavity. And oh geez, I don't even have that written down. I'm sorry. There's one more piece to the definition. It's also where f of x changes concavity. Like literally, that's the most important and most obvious definition for a point of inflection out there. So it's where f changes concavity. So let me draw a couple curves here for us. So let's go with first that one. Let's go with that one. Go with that one. That one. So on each of these 4 graphs, there are clear changes in concavity. Looking here, we've got concave down, concave up, concave up, concave down. The point of inflection will be somewhere in there, the point at which the concavity or second derivative zeroes out for a moment so that it can change from concave down to concave up, or concave up to concave down, depending on the curve. Likewise, over on the right side, it's not as obvious, but there does appear to be a point of inflection right there and right there. Concave up, again, if we imagine finish it all off, we could see concave up and concave down from there. The reverse is true in the lower one. And more importantly, the reason I bring this up is that these are actually things we've seen before. These are what we always called slides. They're slides, places where you have like a triplicate factor, like you have x minus 3 to the 3rd power. We create a slide. Well, when that happens, we end up with not a maximum or minimum, but a point of inflection. There's a place where the graph actually changes concavity. And although you haven't necessarily thought about it, you've actually been doing this for a while. When you draw those little slides, you're literally creating a place where the graph changes concavity as you pass through that point. So for the moment, just know that these are really important. They're a tool or a property of a function that we're going to ask you to find all the time, no different than a relative maximum or relative minimum. For the moment then, I just want to jump in and actually take a look at an example and get you started with seeing these things, as well as getting some ideas in your head. So here we go. Our next example is to ask you to actually go through and find a point of inflection. You can see I'm already using the abbreviation point of inflection for POIs. So we want to find the x-coordinate of any points of inflection of f of x equals 3x to the 5th minus 10x to the 4th. And we are to justify our answer. So in looking up here, I'm not going to write out a plan here because I think it's a pretty simple thing to go through. Anytime we talk about points of inflection, your mind should immediately inflect to thinking about the second derivative. That's just a good starting point to go with, especially if you're given a function. The second derivative is your key to determining points of inflection. So for us to get there, we need to do a little differentiation. It's going to be 15x to the 4th minus 40x cubed. And then that means f double prime of x is going to be equal to 60x to the 3rd minus 120x squared. And if we factor that out, since we're on the second derivative anyway, we'll get 60x squared, quantity x minus 2. So there is our second derivative. From there, a good rule of thumb is to try to figure out where this thing is equal to 0. And that will give us both x equals 0 and x equals 2. So these are what we'd call our critical numbers of the first derivative, or our potential points of inflection. Now I keep saying these are potential points of inflection. And you'll notice that I'm actually going to go through and do a sign chart here. And the reason for that is that most people make the mistake of just going done and labeling both of these as points of inflection. But the truth is that's not always true. These are just potential points of inflection. No different than you can have a critical number where the derivative is 0, but there isn't a relative maximum or relative minimum on the graph. So take a look at what happens with our values of f double prime using those two values worthy of investigation. So I'm going to go 0 and 2. So we know the second derivative is 0 for each one. We want to look at values greater than 2, values between 0 and 2, and values less than 0. So in plugging in some numbers, I'll plug in -1, 1, and 100. When I plug them into my derivative, though, and I'm going to actually make a big deal out of this, when I plug these values into my second derivative, the 60 is going to stay positive no matter what. And the x squared, by virtue of having an even power, is going to be positive as well. So for instance, when we plug in -1, we'll have 60 times -1 squared. That's a positive 60 times a positive 1. Then when we multiply by x minus 2, -1 minus 2 is -3. So we actually get positive times negative is negative. Likewise, when we put in 1, we get positive 60 times positive 1 squared times -1 also, or times -1. So in this case, we get positive times positive is -2, which means we didn't actually change concavity at x equals 0. You would have thought we would. Everything else had that marker. But because of that even power, what we would call that bounce in the second derivative, the second derivative stays the same signs. So it turns out that there's not a point of inflection at x equals 0. Now on the flip side, if we put in 100, we get positive times positive times positive. So we do end up with something positive, or a second derivative positive at x equal, or for values greater than 2. But the important thing here is that the only points of inflection we have is at x equals 2. And our reason, which is the thing that you need to get into your head sooner than later, is because f double prime changes signs. And changes signs specifically there. So the moral of the story here is that the definition is a kind of reminder. It's a cautionary tale, if you will. You cannot say that there's a point of inflection if f double prime of x equals 0. The reason for that is it is possible that you could have a spot where the concavity does not actually change signs, but the second derivative is momentarily equal to 0. Now it's a valid question to ask what this actually looks like to see if that might help you realize why we only have the one point of inflection. So we have 3x to the 5th, 10x to the 4th, 3x to the 5th, x to the 5th, 10x to the 4th. Okay, so here's our function. Let's turn off some of this other mess. So x equals 0 is the place where the concavity went from negative to negative. Notice, although we aren't, you don't know exactly what's happening in there, it looks to me very clearly like this is concave down that entire while. In fact, let's see if we can see anything with the second derivative. There it is. So the second derivative is negative. It hits 0, and then it comes back down and stays negative for a while before hitting an apparent point of inflection, which I think was what we had, and then moving forward from there. So it looks like we did do everything correctly on this function, but again, take this as your warning. There are points of inflection where the second derivative changes signs, not just where the second derivative equals 0. Okay, with that in mind, now that we have points of inflection ready, we can move forward a little bit further and take a look at some other situations that might pop up. So in particular, what I want to talk about is how we can use the second derivative to determine whether or not we have a relative maximum or relative minimum. Now, this doesn't mean that you no longer need the first derivative test. In fact, anytime you're provided the tool or using the tool of the first derivative, you might as well just use the first derivative test. But if you have a very convenient access or a lot of information about the second derivative, there is an additional test that might allow you to declare and determine whether or not you have a relative maximum or relative minimum using that tool instead. So first and foremost, what does the second derivative test say? And if there is paper for you to pass it out, feel free to pass it out now if you haven't already. So the second derivative test says, let f be a function such that f prime of c equals 0, and the second derivative of f exists on the open interval containing c. So we're saying that we've got a place where the first derivative is equal to 0. Ooh, that's important. First derivative equal to 0. That tells us, of course, that we're talking about a critical number. So we're at a critical number on the graph of f, and then the second derivative of f exists on that open interval containing c. Doesn't have to exist at c. Excuse me. It doesn't have to exist at c, but it has to exist around c for sure. Now what it says are three things. It says first, if f double prime of c is greater than 0, then f of c is a relative minimum. If f double prime of c is less than 0, though, then f of c is a relative maximum. And then finally, if f double prime of c is equal to 0, meaning the second derivative is 0 as well, then the test fails and you have to use the first derivative test anyway. So this is a distinct possibility, so don't think that it's never going to come up that way. But let's think about what might actually be happening here. Let's try to visualize what the second derivative test says. So first, we already mentioned that this implies that f has a critical number at x equals c. So we're interested in trying to determine some information using the... excuse me. Jeez. So we know we're at a critical number, so we know we're at a place where the derivative is equal to 0. So there's a horizontal tangent at each of these places, and we're trying to use the second derivative test to somehow clarify whether or not that corresponds to a high point or a low point, or neither possibly. So let's start here. If we look at the first thing, we know that we've got a critical number, and then it says that f double prime of c is greater than 0, which means f double prime of c is positive. Well, if f double prime of c is positive, then that means that f is concave up. And we know what concave up functions look like. They kind of look like smiles, or happy U's, parabolas, positive parabolas. So now in here, if we look at that graph, and we think about the fact that it's concave up everywhere, and we want to look at specifically the point where the first derivative is 0, since we're talking about critical numbers, we can see very clearly that this leads us to having a relative minimum. And it might take a second for you to catch on to the fact that there is a relative minimum there, or at x equals c, simply even though the concavity is positive. But think about it. Positive concavity means the tangent line is always below, so you're going to be able to get to a low point, not an actual high point. On the flip side, if we look at the second statement, if we are told that f double prime is negative, then that means that f is concave down. So in other words, we have a sad face. We have a quote-unquote sad panda situation. From there, if we're at the critical number on a concave down function, then our tangent line has to be above the curve, and therefore we are looking a relative maximum square in the face. So in other words, once again, our concavity actually gives us a really quick path to determining max or min. If the second derivative is negative, a quick draw would clearly show us that we could have a maximum, and if f prime is positive, the function opens upward, which means that we have the possibility of a relative minimum. Now that third scenario is just kind of like, it's not an easy one to work with. I'm trying to see if I have anything. Yeah, in my notes I wrote, too bad. So if the second derivative is 0, you get something where you just have to use the first derivative test. And in fact, although we didn't go that way, in this particular case, notice that the second derivative did not actually help us at either of these two values. So we ended up with I think it was a maximum at x equals 0 on this one, not that we knew it coming in. But we weren't able to use the second derivative to determine it. So in this case, we just need to use the first derivative. Check values of the first derivative around that point, that critical number, and then move from there. So if I were to try to kind of wrap this all up in a bow before we demonstrate it in a second, what we have is concavity at critical number, because again, that's what we're really talking about here. We are at a critical number for a function f, and we have its concavity. That one will tell us whether we have a local max or min. Again, with a few caveats. Like, don't get too excited. Yes, there are some situations where it doesn't work. But in other words, we now have an extra tool that's out there. So this is the moral of our story. And this is what we call the second derivative test. It is the follow-up to the first derivative test that talked about relative maximum and relative minimum in dealing with sign change. So there is the second derivative test. Again, I think your best bet when you're working through this is to remember that the second derivative test requires a critical number, and then once you've got that, to just simply draw a picture representing the concavity of the curve. I think then it's pretty easy for you to tell concave up or concave down, maximum, concave up, minimum. I think that helps quite a bit. So there is the gist of what we're talking about here. Okay, with that said, what I'd like to do next is look at the sort of context where you might pop into or run into a situation involving the second derivative test, while also, of course, going back to some of the things we've done already. So what I've got is I've constructed a numerically based function, or a function that's defined numerically, so you're given a table of values, and I've asked you two questions about it to kind of reiterate some of these pieces. And if memory serves, this is going to be the last example that I do for you. After that, I'll just have a try it left for you to wrap this up, and then to start working on your problem set, or whatever else might pop up. So in our situation here, the table at right gives values of twice differentiable g of x and its first two derivatives, presumably g prime and g double prime. The first question asks, does g have a local maximum, local minimum, or neither at x equals 3? Now, for question A here, to start attacking A, it's important to note that anytime you're given information about the second derivative and asked about maxima or minima, it oftentimes does mean that you're going to be using the second derivative test. That's just kind of it's the right ingredients there. So, it's like if someone's got maple syrup, butter, and, I don't know, batter behind them, you're probably going to have pancakes. Like, just read the room. So in here, in the first one, does g have a local max, local min, or neither at x equals 3? So what we're interested in this case is what's happening at x equals 3. Well, it doesn't matter what g of 3 is equal to. That's irrelevant to our discussion. Like, we know that you can have relative maxima that are really, really low or really high depending on what's there. What's interesting here is that first, g prime of 3 equals 0. So right in here we have that g prime of 3 equals 0, and that is essential because for the second derivative test, we have to have a critical number. So basically that is true right off the bat. That's our first piece of information. In addition, we also then have an opportunity to look at the second derivative. So g prime of 3 being equal to 0 makes this eligible, and then g double prime of 3 is equal to, according to the table, -5. -5 is clearly negative. So that means that we're actually looking at a situation where we are concave down at a critical number. So from here, I'm just going to narrate that. Thus, Thus, g is concave down at critical number x equals 3. So that means, let's think about this. Concave down, critical number, that looks like we have a maximum. So g has a local maximum at x equals 3. So, and at this point, let me point out, like, this answers all our question. We have our stuff. We have that there's a local maximum at x equals 3. As far as our justification or our why, our justification was really this work right here. It was stating those two pieces of information. That was enough to justify our work. Some people, though, feel uncomfortable just kind of stating those things and then going forward and declaring it. If you do, you could always finish this off by saying, by the second derivative test. Like, there's absolutely nothing wrong with that, just to kind of clarify it a little bit more. But truthfully, as I said, the underlined portion is what you had to say in order to justify your answer to part A. So again, this is our second derivative test. Here's some info about a function. Make sure you got a critical number. Check what the second derivative is there, and then conclude whether you have a max or a min. So pretty straightforward. And let me point out really quickly before we go and approach part B, that if you're looking at this thinking, oh, well, I could just use the first derivative test, couldn't I? The answer is no, you actually couldn't. Based on what's here, you might first look at g prime values around it. Well, g prime is negative on both sides, so there's nothing that indicates for sure that we're going to have to have a particular sign change there. But more importantly, just because we know the values at 1, 3, and 6 doesn't mean we have any idea what's going on in the middle. For all we know, this might have a local maximum right at 3, and then there might be a heck of a lot of minima or maxima going up towards x equals 1. So don't get overexcited by the values in the table. These occur at discrete x values, meaning that they're separated. So they're in this case at some counting values. So we don't actually know what's happening at all those real numbers in between. So we can't draw any larger conclusions from g prime in this case. So the second derivative test was our only pathway. Now in addition, let's take a look at part B. Part B tells us that h of x is 3xg of 5 minus 2x. The question we're asked then is the graph of h concave up or concave down at x equals 2. And we are to explain our reasoning. So in order to get there, of course, if we want to talk about concavity, we know that we need to go check out the second derivative. I mean, otherwise, if you want to talk about concavity, I think you'd have to go to a prison and check with their local dentist, because then you'd be looking at a cons cavities. Yeah, you don't know the restraint it took to save that joke for now. But in any event, more calculus related. Oh, by the way, did you know calculus is actually that stuff that gets on your teeth? stuff that gets between your teeth. Interesting connection there too. So back to the problem. Sorry, I'm wandering. I'm really hungry. I haven't eaten lunch yet. If we want to find the concavity of this function h, we need to compute the second derivative. So in order to do that, we need to look at our function, 3x g of 5 minus 2x, and we need to compute its second derivative. So in order to do that, looking up here, the first thing I see is we're going to need to use the product rule. But then I also see with that 5 minus 2x on the inside that we're going to need to use the chain rule. So there's a lot of differentiation here. I'm going to do it, slowly, but I'm going to make sure to move through it a little bit quicker too. So first, in order to get to the second derivative, we need to get to the first derivative first. So in looking through here, I'm going to treat my two functions as 3x and g of 5 minus 2x. So sue me. So the first one will be the derivative of 3x, or 3, g of 5 minus 2x, plus 3x times the derivative of g of 5 minus 2x. Now for the chain rule part, the derivative of the inside is negative 2, so that means the derivative is going to be negative 2g prime of 5 minus 2x. And simplifying that a little bit, we get 3g of 5 minus 2x. Again, I'm simplifying because we're going to have to take a derivative again. Minus 6x g prime of 5 minus 2x. So there is our derivative, h prime. Now we could not be so fortunate as for that to be our function. We want to talk about concavity, so we need to take the second derivative. So looking in here, we've got to differentiate one more time. So our first term to differentiate, 3g of 5 minus 2x, we're again going to use the chain rule and get out a derivative of negative 2. So h double prime will start by being equal to negative 6 g prime of 5 minus 2x. Then on the next one, we'll again need to use the product rule. So looking in there, those are going to be my two pieces. We'll have minus 6 g prime of 5 minus 2x. And then digging into all the pieces, we'll have a derivative of negative 2 coming out. So we'll have plus 12x, because negative 6 times negative 2. And then it'll be g double prime of 5 minus 2x. So again, that's a lot of work to get to that point, but at the same time, at least we're here. And in fact, we can clean it up a little bit, in fact. This is negative 12 g prime of 5 minus 2x, and then it's plus 12x g double prime of 5 minus 2x. So given that, in order to make our conclusion here, I'm going to have to shrink some things, like forgive me for a second. I'm just going to shrink all our work that we've done already. My bad. Okay, I just need a little more space here. So now that we've got the second derivative calculated, our next move is to figure out what is the second derivative at, what was it, x equals 2? I'm going to figure out what's happening at x equals 2. So in other words, we want to compute h double prime of 2. Well, digging in here, if we plug in 2 to the argument, 5 minus 2x, we get 5 minus 2 times 2, which is 5 minus 4, or 1. So we're going to have negative 12 g prime of 1 plus 12 times 2 g double prime of 1. So at this point, we just need to plug in the right values. So evaluating it with what we're given, g prime of 1 is negative 2. So that's going to be negative 12 times negative 2. This will be plus 24 g double prime of 1, which is negative 3. Simplifying this, we get 24 minus 72. And you know what? Although I know that's negative 48, I'm not even going to write it out. What I can clearly see is that h double prime of 2 is negative. Clearly 24 minus 72 is negative. And again, this might be a strategy that's worth taking into your own repertoire. If you're moving quickly or you're not sure you're going to get the arithmetic correct without a calculator, just state it, because you know it's negative. So from there, we know that's negative. From there, that means that we have h double prime is less than 0. So we can write that. Since h double prime of 2 is less than 0, h is, well, as we said before, concave down, means h double prime is negative. So h is concave down at x equals 2. And that contains our justification and our answer. So there is all the work. This is kind of a good, solid, like medium to high level question where you bring some stuff together from a function presented in a unique way. And it contains a little bit of everything today, except for points of inflection. Sorry, I have that question, but I'm saving it for the problem set. So there is our final example. Now from here, I do want to give you an opportunity to work with this a little bit, and just like normal, I want to go through then the problem afterwards, just kind of talk about the solution. So at this point, I'm going to invite you to work through this try it. This try it provides you two rational functions being subtracted and asks you to find concave down, points of inflection, and where there's a relative maximum, and justify it. And you know what? Yeah, let's go for it. So with that said, if you can please pause the video now, we'll give you a few moments to work, and then we'll come back together and go through it. So if you haven't already, please pause the video now. Okay, hopefully you've had time now to work through it and get your teeth sunk into it. Here are the answers, and let's talk about it just a little bit. So for part A, you're asked to find where the graph of f is concave down and justify your answer. It's a pretty typical question, a pretty simple version of the question, but of course there were some challenges in this function. So what I did first, as you can kind of see over here, let's get my pen so I can kind of help myself. Let's get a different color, in fact, two. So let's go with orange. So what you can see over here is first I calculated the first derivative, and I kept it in kind of power rule notation so it's easy to differentiate. Then I calculated the second, and then in order to start working with and finding places where this might be equal to 0 or undefined, I found a common denominator. When I did, I got this expression for my second derivative, which has two places where it's 0, -6 and 6, and one vertical asymptote at x equals 0. So when I set up my second derivative sign chart, I had to break it up at -6, 0, and 6. And then I went through and just checked the sign, like from this simplified version because it was easier to plug into. Turns out it's concave down for values smaller than -6 and between 0 and 6, because of course the second derivative is negative there. After that, for the points of inflection question, I went back to that second derivative and I looked for where it was equal to 0 as a potential place to change signs. And then I realized I didn't even have to do that. We already had enough information from our table. So basically what I noticed was in our table, we could see that f double prime went from negative to positive at x equals -6, and from negative to positive at x equals 6. And of course then it's tempting to say, okay, well those two are both fine, and then also there's a point of inflection at 0. But remember, if we plug 0 into our original function, f of 0, let's make sure I do this right, f of 0 does not exist, due to the fact that there's actually a vertical asymptote there as well. So that means that we only have points of inflection at -6 and 6. And then all that you might wonder about, if you're wondering why I have these ordered pairs, technically it said point of inflection, so I plugged in the values into the original function f and just saw what they simplified to. So and that covered us on part B. For part C, it was a little bit more cumbersome to do algebraically. I spent a lot of time before this lecture trying to come up with a really nice example that worked out numerically pretty. It was very arithmetically pleasing. I couldn't do that, so I just stuck with what was there. So of course we were trying to find the one relative maximum. That meant to start with we need to find the critical numbers. And going back to our first derivative over here, which simplifies to 18 minus x squared over x to the fourth, we could see that there are two critical numbers at plus or minus root 18. After that, what I did was I checked the second derivative of each, plugging in and taking advantage of the fact that the numerator was really easy because we were squaring the number, and the denominator was ugly, but we could tell its sign really easily with the fifth power. And it turns out at the negative square root of 18, our graph is concave up, whereas at the positive square root of 18, our graph is concave down. And as we saw earlier, concave down at a critical number qualifies as a relative maximum. So there is in fact a relative maximum at x equals root 18. And with that, we then use the second derivative test, or invoke the second derivative test to complete this out. And that, my friends, completes the lecture. So, although you might want to pause this here and just give yourself a chance to soak this in, it's all here. And of course, there are video solutions tonight that can kind of help you out. And as just kind of a quick rundown of what we did today, we started by looking at a function and noticing that although the first derivatives where it equaled 0 gave us good information and we knew what that meant, we didn't really understand what was happening when the second derivative was 0, but we could tell that something had to be changing there, and it looked like it had to do with whether or not the curve was happy or sad. And there were also camel drawings that were bad. Beyond that, we looked at the definitions of concave up and concave down to describe the two different versions of this concept called concavity. But although it was easy to see, we could quickly draw out and confirm that these two things kind of matched what we saw, they weren't a very practical definition. So after that, we analyzed what happens with both f prime and f double prime when f is concave up or concave down to see that there were two things that we could add on. The sign of f double prime tells us concavity. So in other words, if f double prime is positive, f is concave up. And f prime is increasing is the same thing as f is concave up. And of course, their alternates are the same as well. So that gave us a more practical tool, and our work today focused on using the second derivative to analyze the behavior, the concavity of a function. After that, we talked about that, or we did an example. Then we talked about the place where concavity changes on f, which is called a point of inflection, or a POI. And of course, we said that the function has to exist there. And then we have to use the second derivative actually has to change in order for this to be a true point of inflection. So keep that in mind. Beyond that, we found some points of inflection and talked about the fact that it's not simply where the second derivative is 0. That just means that you might have a point of inflection there. Instead, we did need to actually check and make a sign chart to confirm that this actually worked the way we thought it would. And then after that, we talked about finally the second derivative test, which basically says if you're at a critical number, the concavity sign, so either plus or minus, will tell you whether or not you have a relative max or relative min, barring, of course, the possibility that the second derivative is 0 as well. So looking at that, it was pretty simple when we drew out a picture. We did an example that involved that, as well as some hardcore differentiation. And then finally, I gave you a chance to work through a try-it that I would say is a pretty challenging problem, like an aggressively challenging problem. With that said, though, other than a blank page, that completes today's lecture. Hopefully this has been good information in a pretty compact form. I'm trying really hard to keep these things as compact as possible. It's hard to do when you're filming in the summer and trying to do things. But in any event, I hope this has been helpful. This will be available for you online, as will video solutions already. And thank you for watching and hopefully learning. Have a good day.